folks. Good morning. Well, the first question is, do we have enough homework problems for this week? Anybody?
Three, four. Three.
Okay, I'm gonna add a little bit. But anyway, we're finally getting into harmonic oscillations. So, good, I'll add a couple and then we can decide on which week they belong to. Okay, so we're doing small oscillations. And we ended up with this result here. Oh, we started with, so we actually started with the energy. Expression. And we integrated it. I left you guys a couple steps in the integration of the energy as a homework problem. And with u of x equals 1/2 kx squared, we find that x of t, a cosine omega t plus, I'll just call it alpha, the phase there, and this omega is equal to the square root of k over m. So we're going to investigate the formal properties of this some more, but I'm still going to return to where this thing came from here. So this k is actually equal to the second derivative of the potential energy at an equilibrium point. And so it's greater than 0 where u prime of x0 is equal to 0. That's its actual definition. And then when you have a spring, so to speak, off the shelf, the way we've learned, we have a mass sliding here without friction with a spring constant. So under those circumstances, I even argued even this ideal mathematical physics spring would have as its second derivative of potential just that constant. Remember I said if you stretch it too far, it's going to break, compress it too far. So I want to go there a little bit more before we leave that and just start studying this here formally. Okay? Because what we've spent a bunch of time doing now is understanding where these things come from. And there's a nice example of this that we can add to our, actually I have two good examples. The first example is just going to be if we hang this spring under the influence of gravity. Okay? So instead of having it horizontally without friction, we hang it here. What's the potential energy of this system now? Okay. Well, the spring has an unstretched length. Okay. And then when we attach a weight to it, it stretches and then it comes to a lower equilibrium. Okay. So everybody's seen that before, right? You have a spring, put a weight on it, it stretches. And the question is, what is the motion of this system compared to this system here? And what we can do is, graph u of x, because what that u of x is going to be, it's going to be mgx plus 1/2 kx squared, because it's got the gravitational potential energy and it's got the elastic potential energy of the spring. What do you think? You guys agree with this? So this mgx is just the position of the spring. I better put an x-axis here. Position of the spring in the vertical x-axis. that's the, but not the spring, position of the mass, gravity, gravitational potential energy, but the spring is also compressing or stretching. Question?
It's actually irrelevant to the equilibrium position.
We'll find that in a moment. Okay. So this actually, the x equals 0 has to be at the, I'll put it right here. The x equals 0 has to be at the unstretched spring, right? That's the 0 at the unstretched spring. So there, what's the graph of this? You know we love graphing things. So the graph of this, you know, it's the sum, let's do this here. It's the sum of a straight line and a parabola. And what that does is it just really shifts the parabola to the left, like so. Right? And we can call this x of 0, because that's the new equilibrium point. And notice it's on the left side of the axis here, that's fine, because this thing was pulled down a bit, came, you know, if you just held it gently, lower it, it comes down to some equilibrium point down there as well. But if you've all seen this, you know, it'll bob up and down. You didn't have to bring one to class for that. And the question is, what's the new frequency? Is the gravitational potential energy change the frequency? Anybody want to have a stab at that before I? The frequency is still according to this definition. Okay. So what's the second derivative of this potential energy function? K. It's K. So we get the physical result that the equilibrium is shifted, but the frequency remains the same. And this generalizes to any constant force. So if you have an oscillator, you apply a constant force to it, it just shifts the equilibrium position, leaves the frequency unchanged. So we can actually, so I'll just write here, because U double prime equals K, comma, we see that a constant force shifts the equilibrium, leaves the frequency unchanged. Constant force shifts equilibrium, comma, leaves frequency unchanged. Good, so that's a nice, very basic, but nice analysis. And my second example, I'm going to erase. You guys have this? Yeah, I'm going to erase. And the second example, sort of a machine that we can imagine building. We can get Matt Bowe to build it for us, but we're just going to look at this as a theoretical idea here. But what we have this time is a mass on a track, so this is going to be the x-axis, it's going to be the origin. But this now is a top view of a mass on a track, and what we're going to do is connect springs in this direction. I'll leave that origin there. Okay, so there's N. We're going to connect springs like so. If you guys visualize this, we pull it forward and it bounces back and forth. It's connected by springs in this direction. So each of these two springs has a spring constant K. That's what we paid for, spring constant K. Now we have to be careful here. So we're going to have a distance A, but the springs have an unstretched length springs K have unstretched length L. Unstretched length L, and we'll say L is less than or equal to A. So if L is exactly A, then I'm just attaching springs here and here, pulling on it. If L is less than A, I actually have to stretch them a bit to attach them, okay? So what we're gonna do is construct the potential energy function of this as a function of X. See, if I stretched them to hook them up here, they already have some energy in them, right? I put a little energy in by stretching them. Then as I pull on it, they're gonna have even more. And it'll be pretty clear that, you know, if I pull it over to here, the force is to the left. If I pull over here, the force is to the right. So let's see what that function will look like. The potential energy of X, there are two springs, so it's symmetric. 2K actually 2 times 1/2 K, and I'm just gonna say L squared for the moment. So what do I mean by that? If I drag this thing out to here, then I have the springs attached like that. We're not done with this, okay? So the length here, this L of X, but the amount they've been stretched is L of X minus lowercase l. Okay. The unstretched length is L, the stretched length is capital L. So we have 1/2, so 2 of 1/2 K, make the right color here. We have L of X minus lowercase l squared. That make sense? So there's two of them. And when I stretch this spring, here's the blue line. The amount of energy in is the length minus the unstretched length, because that's my delta length squared. So let's clean this up a bit. We have, first thing, a good thing to do is to take the 1/2 out. We want to keep that standard form. Well, what's the L of X? So there we have the Pythagorean theorem. You know, we have a squared plus x squared, right? A squared plus x squared equals L squared. So L is equal to square root of a squared plus x squared. So maybe I'll turn that around. Square root x squared plus a squared minus L 1 squared. So I'm gonna make the rest of this problem a homework assignment. If A equals L, then when x equals 0, this whole thing is 0. But that doesn't matter. What we want to do is get so homework here. Expand u of x to second order. Third and fourth order is a mess. We've done that before, but we're going to expand it to second order. That means we're just looking at u of x equals u of 0, u prime of 0, say. Second order is up here. And you will find that that's zero, right? The first derivative vanishes. So this is the first non-trivial thing here. And so that's the first thing to do. And the second thing is to find the effective spring constant. So find, we're just going to call it K effective equals U double prime of 0. What else will we find here? So we get the second derivative of this thing at 0 very carefully. And you're going to find that, so I'll just put it here just to make sure. Show that U double prime of 0 equals 0, comma, when L is equal to A. So what's nice is this is a machine here that if you hook it up with the L equal to A, it no longer has harmonic oscillations. Okay. If this, if this effective constant, if this thing is 0, your next term would actually be a fourth order parabola, so to speak. And under those circumstances, you don't get harmonic oscillations. The harmonic oscillations come when you actually have quadratic. So this is good. I've actually assigned the third and fourth derivatives in the past, but the third one's going to vanish the fourth, so it's a bit of a mess. So this is a good assignment right here. You find the effective spring constant and find that. And with the effective spring constant, it's really only true for small oscillations. If you pull on this hard enough, it's no longer a simple parabola. But it is parabolic right down there around the origin. Okay, good. So we'll have to see what our homework list consists of now. For Friday, actually we can consult now. What do we have the whole entire homework assignment for this week? Let's see how many of these.
There's A over x squared minus B over x, and find x naught such that U double prime equals 0. Then have U double prime x naught bk.
Right. So we have this A over x squared plus B over x
Minus B over x.
minus B over x, that's right. And what else do we have?
It's also finding the limit of t sub n as n approaches infinity for the
Yep.
dimensionless integral.
Yep, okay, good. T sub n, and goes to infinity, that was only 2. Is there more?
We also have show that with W is equal to the square root of K over M.
Oh, the inverse cosine? Or do that integration with the cosine?
I mean, if you do the integration
Say
of
do a trick
square root
substitution.
k squared minus x squared, you
Yeah.
get inverse sine, not inverse cosine.
Minus sign will do the inverse cosine. So you can do the trig substitution with a minus sign. Remember we have plus minus in front of the integral, that'll get you so you can get both, inverse sine or cosine. Yeah. Okay, so we have that trick. Okay, so if there were only those 3, then the 2 I just wrote up are perfect for the rest of the week. So we'll make these 2 homework problems. The one I just did.
I think with that one it makes
4. That's right, because I did that thing for you. Okay. Possibly we'll add one, but we'll definitely do this one. This is a really nice one. You know, you've been doing Taylor expansions and derivatives and stuff. This one is right in that vein. Okay. Okay, good. Those are some good problems. And now what we're going to do, so, we've got some good physical insight on all this. Now we're just going to go back and study this thing and some of its properties. So the difference now is, we're just going to study this and assume these things, right? We don't have to, what we did on the previous problem, we're actually figuring out what that K really is. Okay? And those other ones, for example, that A over X squared minus B over X, that's just doing the second derivative criteria, okay, to find K as well. So now we are just gonna accept this thing and look at these harmonic oscillations and their properties. So, harmonic oscillations. And let's see, we can, first thing we'll do is take this expression here and expand it out. So we have x of t equals a cos omega t cos alpha t. How do you say cos alpha minus a sine omega t sine alpha. So I just used the addition formula for the cosine. So if we clean this up, we have a cos alpha, I'll put parentheses around this, cos omega t, cosine omega t, plus negative a sine alpha sine omega t. Or you could use different letters and you could say, or x of t, very generally speaking, a cos omega t plus b sine omega t. Different a. The point being that these are two fully equivalent ways of looking at it, because with a positive constant and a phase here, you can express any function, I mean any number. Okay? So we can express any numbers a tilde and b tilde with this a cos alpha and this negative a sine alpha. So that's fully general and equivalent, and of course we can drop these tildes here. I'll just be, okay. So yeah, these are fully equivalent. And the next thing, this is a solution to a second order differential equation. So as we see, it has two undetermined constants. Now, for motion, we typically have as the constants the initial position and the initial velocity, right? So what about initial position and initial velocity? So we have initial position x of 0 equals x of t equals 0. Well, we can see right here that is simply equal to a. And initial velocity, we would have x dot, we'll have minus omega a sine omega t plus omega b cos omega t. So the initial velocity at t equals 0. X0 dot or V0, what do we get here? This one's gone. We get omega times B. So we can make that substitution back in here, and we can say we would have had x of t equals x0 cos omega t plus v naught over omega sine omega t. So yeah, these are all equivalent forms. And that's why once we, you know, if we're doing small oscillations, we get here, we just declare we're done. Okay? Unless we need some other special fact. This original one here is fully general, right? Is adequately general, but this would be specific initial conditions that we could plug in. So what else about harmonic oscillations? They come from energy conservation. We're gonna see, probably not today, but soon. As soon as you add any friction into the system, you no longer have energy conservation, and you get damped oscillations. But for the moment, we had conserved energy, and let's investigate the energy for these oscillations. Oh, actually, I'll just put it here as a note that I hadn't, but mentioned originally. Period T is amplitude independent. Amplitude independent. Okay. And this has to do with that squared. Remember we had x to the n, and only n equals 2 of the amplitude independence. Okay. Here's amplitude independent if the potential energy is quadratic. So yeah, that only came for the power of 2 right here. Okay, good. So we're talking about the energy. I'll mention that as well. So those other, I'll just put this here as a reminder. Remember we had u of x was b x to the n, right? That's what I'm referring to. Only when n was equal to 2, n equals 2. Only when n was equal to 2 did we have that amplitude independent period. The other ones though, n equals whatever, the energy was still conserved. Just want to bring that into play. The energy was always conserved, but only this one had the amplitude independence. So only this one gives you these trig functions. Okay. Everything else is much more difficult to solve, to work with. And yeah. Good, so we're talking about the energy still, and I'm going to write down the energy using this solution here. So this solution and energy of the harmonic oscillator. So, there we have a half m x dot squared plus 1/2 kx squared is equal to E. So that's going to be trivial. 1/2 m, and x dot is omega. You know, you plot an omega. So x dot squared 1/2 m omega squared a squared sine squared omega t plus alpha. And then we'll have 1/2 k, and the x squared will be a squared cosine squared omega t plus alpha equals E. And we have 1/2 m omega squared a squared, and we have 1/2 k a squared, right? Let me write it this way. yeah, since K equals M omega, K equals M omega squared, so I can factor that out. And then I'll have sine squared plus cosine squared. Plus cosine squared equals E. Okay. So yeah, sine squared plus cosine squared equals 1 equals E. So we have for the energy 1/2 Ka squared equals E, and equivalently 1/2 M omega squared. A squared. So that's the energy, okay? That's trivially comes back out because that's what we put in. But then there's a question of the time average of the energy. So I'm going to erase this over here now. So next we're going to look at time average. So the time average of a function F time average is equal to 1 over period integral F of t dt 0 to t. That should make sense, right? We're adding them all up and dividing by the width of the thing here. So if you're doing the time average, what's the time average of one of, put this in here. What's the time average of x of t? So A cos omega t plus alpha. Time average of the position over a full period. Very important. So, I'll just take like that. Call that 0 to t. So that average is up to 0. Okay. Time average of an oscillating function over a period is 0, but the time average of the square of one of these is not equal to 0. So what we want to do is find, so yeah, I'll just put note, time average of x equals 0. Now we're going to do it for the kinetic and potential energies. Good, so we've got that definition. So next, we want the kinetic energy. I started using T for kinetic energy in this class. It's going to bring a little ambiguities into our expressions. We'll use capital T for the period as well. Next, kinetic energy. This is where it starts. Then in Lagrange mechanics, we have to use it too. Kinetic energy, we use the letter T, 1/2 m x dot squared.
We do T sub K just to distinguish it a little.
We could, yeah, we could do that if we want to. T sub K, but it's, yeah, especially when we're about to talk about time averages. It's unfortunate, but it's gotta be, okay, we'll use T sub K. I mean, it's not unfortunate because this is just very standard nomenclature. Just like the dots. So anyway, we want the time average of the kinetic energy. And then that will be 1 over the period integral 0 period. And now we have the 1/2 m x dot squared, but we already know what this x dot is, and we're gonna square it. Omega squared, a squared, sine squared, omega t plus alpha, dt. And the time average of the potential energy is also gonna be 1 over t, 0 to t, 1/2 k, and then again the x squared from over there, a squared cosine squared omega t plus alpha dt. Okay. So it's a very fundamental property of harmonic oscillations that these two time averages are actually the same, or equal to each other. You know, I'm gonna put that on the homework as well. Prove that kinetic time average equals potential energy time average. And since they're both equal, they equal 1/2 of, you know, the total energy, right? Each one equals 1/2 of the energy. Now the thing is, this isn't really that, this isn't difficult. You can go into your old sine squared, right, because you have these boundaries that aren't exactly the same. But it's trivial for alpha equals 0. Okay? For alpha equals 0, it's essentially what we just did. So, because remember, your k is equal to your m omega squared, so you can equate those right away. And, but yeah, I'll have you guys prove it. Like I said, trivial for alpha equals 0 and no problem otherwise. But yes, it's one of the defining characteristics of these oscillations. So one of them was the amplitude independence of the period. The other one, you could say equivalently, is the time average of potential and kinetic energy. So for that reason, it's good to have a handle on these things here. Yeah. But yeah, everything pulls out front. You're just really saying that sine squared over this entire period is equal to integral cosine squared. So whatever way you can do that, no problem. Good. So since we're talking about energy, we're actually about ready to add damping to our oscillators. Okay. These things here are ideal. You know, the oscillation goes on forever, never comes to a stop. In real life, your oscillators tend to come to a stop eventually because they have friction in them. So I think we can start talking about damped oscillations. Yeah, time average property. Anything else? I think this is good. Okay, so let's do this then. Next, oscillations with friction. Now we don't have energy conservation. So we're going to start with the equations of motion. I remember I put the equation of motion up last time. We have mx second derivative is equal to f. Okay. That's the general one-dimensional Newton's law. Then for Hooke's law, so then we would say mx second derivative equals minus kx. Hooke's law. We already know that u is equal to 1/2 kx squared, and that gave us the harmonic oscillations. Okay. So what we're gonna do next is add friction. This was U equals a half kx squared. So that's what we've just been doing, okay, at the level of the equations of motion. So now what we're going to do, is say the mass times acceleration. We're going to have a Hooke's law. We can imagine we've got a spring, but we're also going to have minus b times x dot. So that's a linear velocity dependent friction. Linear velocity dependent friction. Dependent friction. And of course, if b goes to 0, friction goes to 0, we're back to where we started. But this is the one we're going to study. And there's actually an interesting version of this that we can, since we're talking about energy, I think we've got time to talk about the energy here. Okay, I'm just going to rewrite this up here in the following form. So now we can say we have m x second derivative plus b x dot plus kx 0. That's the oscillator with friction. Now we would draw the same picture here. We'd have our ideal spring K, we'd have our mass, be on the x-axis. But you know, now we've got some friction in there somehow. And in fact, if it's velocity dependent friction, it's more of the fluid type of friction. But for small oscillations, this works very well. It's, you know, the kind of friction you associate here would be sticky and slipping, right? So, whereas the fluid oscillation, if you had a pendulum oscillating in air, that's enough to have just a fluid type of velocity dependent friction. Okay. So what we're going to do, let's even try. What we're going to do is consider the energy. So this is the, I'll put some friction here. Oscillator with friction, just so we have it up here for the record. Oscillator with friction. So the energy of the oscillator with friction E is equal to 1/2 m x dot squared plus 1/2 kx squared. And what can we say about that energy just based on the form of this equation right here? We have dE dt is 1/2 m. And now we're going to do the time derivative of x dot squared. We've got a chain rule. We've got 2 x dot x second derivative. And then we have the time derivative of this one. We've got a 1/2 k 2x x dot. Okay, so we'll have some 2's cancel. What we can bring out is an x dot, common factors. Now we have m x second derivative, m x second derivative plus k x. And what does the differential equation tell us about m x second derivative plus kx? Minus bx dot. So equals minus bx dot. So that equals times negative b x is before we even solved this differential equation, we see that the time derivative of the energy is equal to negative B x dot squared. What do you think of that? So the energy is decreasing because x dot squared is always positive. You know, you could do two things. You could say, I'm going to use this to prove that the constant B is positive, or since the B was an opposing the direction of motion force, we can say, okay, we already knew that was positive, and this is telling us the energy is decreasing. The energy of the oscillator is decreasing. But yeah, when you can do this, you really lucked out, because we actually got a real physical result, and we didn't even have to solve the differential equation yet. So the analysis of the differential equation itself already gives you some insight. Which is a good place for us to leave off. What we'll do next time is start solving this differential equation. Good.